So anyway, yeah, this is a talk about a little overview of the kclient code. And I'm not going to go into a lot of real depth here. I'm just going to give you sort of a lay of the land. Or interested in doing some work in the kclient and you want to get started. So the first thing is that when you pull down like a kernel tree, and the first thing to do is to understand what the kclient is. And really what it is that it's a re-implementation of Ceph. So we have Ceph is a big complicated tree that we've all done some work in, but the kclient is really just a copy of all that code. It doesn't really share much with the userland client, aside from maybe a few header files here and there. And so we've got several pieces in the kernel to handle all the Ceph client stuff. And the first piece is Libsep, which is a kernel module. And really what this is just the underlying transport layer for Ceph, for the Ceph code in the kernel. And so here, all of this code is contained in netceph, or most of it is anyway, aside from a few header files that are under an include directory. And then, in here you can see that there's a bunch of stuff that you can probably pretty much sort of understand from the names. There's parts for handling auth and the authentication. There's some stuff for handling crypto. The messenger is here, and there's v1, v2 variants. We have an OSD map. There's the OSD code, client code, the mon client code, stuff for handling OSD and mon maps, et cetera, right? So in any case, we've got all this code basically lives in here. I'm not going to go over this in great detail, but I'll talk about a couple pieces of it here in a minute. Aside from that, we have two more pieces in the kernel. There is drivers block rbd.c. And so this is the RBD driver. It's not very big, but it just calls down into Libsep to do most of what it does. So this is how the Ratus block device is implemented. And so you can see here, there's it's mostly self-contained into a single file, and it's not huge. It's like maybe a couple thousand lines, maybe. Let me see. Or 7,000 lines, excuse me. And then we've got FSCeph, which is where all the CephFS code lives. And this is a complete VFS layer kernel driver for the Ceph client. RBD, when you look in there, what it's doing is it creates a block device driver. When you think of file systems in the kernel, they are themselves drivers basically for those as well. And they, this also will call down into Libsep to do most of the traffic that it needs to do to talk to the various daemons that it needs to talk to on the other end. When we are dealing with a file system, most of what we are doing is responding to user-driven events, things that come in from, like, say, syscalls, or it could be NFS activity or NFSD activity, or SMBD activity probably these days. Any of that kind of stuff is we are essentially we call most of it comes in through the VFS layer. And the VFS layer has a bunch of, is essentially object oriented too, just like, sort of in a poor man's object orientation, like a lot of the kernel is. But anyway, there's a main file for that sort of, lays out how VFS objects are put together. Let's see, so essentially, in fs.h, include Linux fs.h, we have a bunch of different objects. The canonical one for the driver is this file system type thing, and it has operations, a couple of operations vectors in it. One for initfs context. There's a mount, which is for the old mount API, and there's kill SB here, which will kill the super block eventually once you're ready to destroy it. From a file system type, so what happens is when you go to mount, right? The kernel will create a thing called a VFS mount object, and then we end up with So then we end up with a struct superblock object, and this thing, superblock, is what represents a file system in the kernel. And so we've got a bunch of fields in here, and a lot of these may look self-explanatory, but in particular, we've got a CephFS Info. This structure here will end up pointing at what we call a CephFS Client. So in this generic superblock, we'll have a generic pointer that's void star pointer, right? And it points to some superblock info that we've got for Ceph. From here, we've got two main things that we deal with. There's a struct entry. There might be in a different file, actually. Here, I'll do The big one here is Struct Inode. So this represents an inode in the kernel. And these structures are usually embedded inside of the Ceph Inode Info. So the superblock is a little different. It has a pointer to a private info. When we get down into inodes, what we do is we embed them. Then from here we've got So here's a struct entry, which represents a path name component in the file in the superblock per superblock. Linux actually has probably the most advanced entry cashing, or lookup handling, entry handling info or method in the world. It's probably one of the places where it really shines, and compared to anything else that's out there. But in any case, we have a bunch of these entry objects in here too that are also somewhat managed by the MDS. And then it also, as you note here, has a specific pointer that points to some void objects that we'll get to later. From here, so each of these VFS layer objects generally has, in addition to this, So each of these structures usually will have. Oh, there's also struct file, which represents an open file. I'll go look at that right now. Each of these operations, or each of these structures usually has a operation struct hanging off of it, and this is sort of where all the class methods for the thing end up being, right? So you've got here a bunch of dispatch operations for various things, like for lookup, right? If you want to do a lookup in a directory, when we go to do the lookup, when you go to do the lookup, it's going to call this lookup vector, right? We've got a bunch of other stuff in here. There's create, right, to create a file name, link, unlink, symlink, all this stuff. Whenever a syscall comes in, we end up usually doing some path name walking to go do lookups in there, and then we end up calling a sort of a terminal operation that will actually do the stuff we want to do. One of the particular ones to note is this atomic open. So for network file systems in particular, right, is that usually, like when we go to do to open a file on a local file system, we're going to go do a path walk down to where the thing is, look it up, turn it into an inode. Excuse me. And then we will turn around and issue an open call against the thing. Atomic open, but that's a bit of a waste for a network file system, right? Because if you have to do a lookup and then go back and open the thing, that's two round trips to the server, right? So we don't want to do that. What we'll do is we instead will just issue an open request, right? And if it comes back with an enolint or whatever, right, then we just say, okay, well, this entry just didn't exist. And then, so we have a combined lookup and open call here. in atomic open. But in any case, you can see all this stuff. Some of these things too are somewhat block device specific as well, like FIMAP, that sort of thing. And so for those, we just generally don't. And if you don't define these operations, usually what happens is you get either some generic error back, or if they're set to null, then you'll get back a generic error when you try to call them, or it will have some sort of fallback code that will do something different. And so each of these objects has these inode, these operation structures hanging off of it. There's an inode operations, there's file operations, there's another one for dentries, there's another one for super blocks too, super operations. Yeah, here's the super one for if you want to mount, unmount, do that kind of stuff. Create new inodes in the super block, because the inodes can be different sizes for different file systems, so we have to have an allocator, a method in here as well. Now let's talk more about the specific stuff in Ceph. So like we were talking about, right? Most of the info for the Ceph client is in super.h, fsceph super.h. And so here's for instance, is the Ceph Inode Info, right? Which is the inode representation for a Ceph inode. And if you see in here, there's basically we have a bunch of fields that are Ceph specific. Layout info, say, and and there's stuff for caps here, an RB tree to hold cap structures, which we'll talk about a little later. And then finally, you have down here where the VFS inode is actually embedded. Note here that we actually embed a full VFS inode in the end of the thing. So when you go to allocate an inode, you essentially get all this junk at the top, and then the VFS inode allocated at the bottom. And you can see here too, we also got some if-def out pieces like this. If you don't compile in with FS cache, you won't get this field in here because we don't need it. That sort of thing. From here, also we've got, when you go to mount the thing, right? So per super block, when we go to mount, what happens is we open a bunch of sockets to different servers, right? We have to open them on first, figure out where the MDS is, then we go talk to it, and then we go, might have to go fetch some stuff off an OSD later. And so at the super block level, we have this CephFS Client struct, and it actually points to another thing called the CephMDS Client, right? Which is actually the part that talks to the MDS. So, and then we've also got some things in here like work queues, cap work queues, that sort of thing. And again, if-def out pieces, and if you don't compile with debug-fs, you won't get any of this stuff. You get with fs cache, you'll get. The interesting bit here is in the CephMDS client, where that's defined. I'm trying in this file. Hang on, I gotta figure out where it is. So anyway, we'll have a here it is. So in the CephMDS client, this is the thing that represents our connection to a particular MDS, to the MDSs as a whole. And so you can see here we've got a list of sessions. Here are an array of sessions. And then there's also in each session, CephMDS session. And each of these guys has a connection as well. And this thing is dials back into Libsep, and then that represents the connection to the Ceph daemon on the other end. And now the Ceph connection. Apologize for being all over the place here with this thing, but it's a little. There are a lot of pieces here. essentially has a a socket here that that represents the actual TCP socket that it's going to talk to, that uses to talk to the daemon on the other end. And there's some other fields in here too. One of the interesting bits here, we have this sort of unfortunately named mutex in here. Pretty much everything is done under this mutex. The Libsep code is highly serialized, probably unnecessarily so, and it seems to probably, and my suspicion is that this kills performance. So one of the things I'm actually looking at doing right now, or have been looking at over the last month or two, is trying to at least get some pieces of the activity out from under this mutex, so we don't need to serialize quite everything. In any case, so let's look at what happens. Let's say we've mounted a file system, and now we're going to go. We want to do open a file, maybe, and write to it. Okay, that's probably a pretty simple sort of operation that we do. So the first thing we're going to do, right, is we're going to call into the walk down the path till we get to Ceph, into the CephFS, and maybe walk down doing lookups as well for different path components till we get to the file we want to open. And so in that directory, in the directory where we're going to open that file, we're going to issue an atomic open. And so when you get the atomic open, you get a bunch of different parameters. Here's a directory. Here's the name of the entry, which is the the entry that we want to open. Here's a file that is not quite filled out yet because we haven't actually done the open. And then there's some open flags, and then a mode for the, if we're doing a create and the UMass mode. So essentially what we'll do is walk down this thing with, if we've got more than name max here, which we should send back name too long. But then we've got some other stuff too, like if this thing is a create, we're going to do some some setup, and then we if we're not being looked up, then this is negative. So there's a whole bunch of rules for doing atomic opens. It's probably more complex than it needs. Alviro has been raging about this for years, but he just doesn't want to change out how it's going to work. In any case, eventually though, we're going to come down here and we're going to prepare an open request. So this is actually the request that we're going to send to the MDS to say, hey, we want to open this file. And so we set up some stuff here. Again, if we've got an ocreate, we might just try to do an async open, depending on whether we can get away with it or not, if we've got the right caps. But eventually, let's pretend for just a second that we're not going to do an async open. And then, so we'll just go down to here. We fill out the request, this MDS request, which is what this rec thing is here. And then we submit it to the engine to do its thing. And then eventually, this is a synchronous request in most cases, or definitely a synchronous request here. And then we end up, when the error comes back, if we get inoint, we say, oh, that file doesn't exist, and we send it back to the kernel to say, hey, no, that file wasn't open, or this file doesn't exist. Or otherwise, if we've got a ocreate, so we've got a bunch of rules here that happen here. But at the end of it all, we will call this finish open, which will finish filling out the struct file. And then, let's say we've got at that point, we've got a fully instantiated open file. It'll get hooked up to a file descriptor by the generic open handling code, and then pass back to the user. So now let's say that we've done that, and now we're going to issue a write. So the first thing it's going to do is it calls this function, it turns this write into we have this sort of generic iterator called an IOB iter. And so we get a write request from user land, or maybe from a splice request, or who knows what, right? But it gets turned into this IOB iter, and it says, write this data to this, to these positions in the file. And we've also got this IOCB, which is sort of an IO context. And so the first thing it's going to do is look in the IOCB and say, okay, here finds the file. This KI filp is what points to the struct file. And then from that, we can get the inode that we're going to talk to, et cetera, et cetera, et cetera. And we do some other checking. A lot of this stuff is doing. If we're trying to do an O append, right? It will do this, do a get outer to try to get the size for the file. This is terribly racy, so, but it does sort of semi-work. And we also will check to see if we've got an OSD, a full OSD. And if we do, the deal is that we want to do a synchronous write in that case, right? Because we never want to. So Ceph is, if we've got the, well, here I'll talk about it. But in any case, if we've got this, then we're going to want to do the write synchronously. If it turns out that the thing was setuid file, we have to strip the setuid bits. And then what we do is we start checking for caps. So the next thing we do here is we call down and we say, okay, we're going to get caps, and we have to have file, the FW caps, file write caps. But we also want file buffer cap, or maybe lazy IO cap. Now the MDS will issue these, FB caps if it wants to allow the client to cache or to buffer writes. And if this is the case, then we can go down here. When we get down here, also like here where we increment the I version. But down here we we'll look and see. Okay, did we get these? Got represents what caps we got. And if we got the file buffer, didn't get the file buffer caps, we're going to need to do all of this synchronous. Same thing if we're doing an O direct write. We can't use the page cache there. Same thing if we're doing the thing was opened OSync, or we've got or there's been an error, a write back error recently. If we've got that, we also switch to doing synchronous writes. So in any case, we come down here, we get some snap context info there, and then we come down here and call, if we're doing a synchronous write, we're going to call down into here and do this. If it's a direct write, we do this. If it's a sync write, we do that. Now this code path is not commonly traveled. Most of the time, the client has caps and can use the page cache, which is good because that helps performance. But when it's not, then we actually have to go and issue a synchronous write to the server. In any case, from there, we will call, but let's say we have caps. We're going to do a buffered write. We call into generic perform write, which calls back into the VFS. And the VFS at that point will call something called write begin. We use Ceph write begin. So in addition, every inode also has what we call an address space. And so here we can do when we're using the page cache. Now, when we don't have caps, or we're doing particular types of writes like O direct or whatever, we don't use the page cache. But when we do, we have to call into operations here. And so the first stop for this is Ceph write begin. And what this does, we'll go and try to fault in the page. So, and we've seeded a lot of this code or moved a lot of this code into the netfs layer now. But effectively what it does is it calls in, and the netfs layer now, we have this set netfs readops. And it has a bunch of operations to do things like issue read operations. We also can resize them, that kind of thing. So we've moved a lot of the boilerplate code that was in here into this. But the interesting bit is this netfs issue op. So let's say we're going to do this non-buffered write, or this buffered write, sorry. The first thing it's going to do is if we're writing to the page, we were given a page, so write again. So here we're given this page, and now we have this, we have struct folio now, but essentially struct folio represents a page at this point. And what we will do is, we're given a page here, and we have to go and figure out where this page is in the file, and then down here we call into netfs write begin, and if it looks like we need to, that we're going to have some parts of this page that are not written in this write request, then we're going to go and, that's what I wanted. We're going to go and do this operation here to fill it. And so what this does is that, I should say, if anyone has questions, please speak up and ask. You don't have to wait for me to stop talking. Does anybody have any at this point? Okay, I'll take that as a no. So in any case, we have this OSD request that we do here, and so we call down to CephOSD new request, pass in a whole bunch of parameters based on what we're trying to do, which is read do a read, and then we're building a read request here, and then we also build this IOD or X array, which is I won't go into right now, but in case essentially this is the thing that holds all the pages. Or represents a bunch of or represents and a range of the file. And then we have this IOD iter get pages alloc, where we allocate an array to hold the page structures that we're going to fill. From there, we pass that down here to sort of set them up in the request, and then we go ahead and start the request. And so this thing will then go turn around and this will start the request running, and then eventually, once it finishes, we will call this finish netfs read function, which will then go and handle whatever it was. So when we pass this thing down here to the Libsep engine, what happens is we've given the Libsep an array of pages and said, okay, plop all the data that you read into here. And so these pages will end up being written to, populated, and then we call this finish netfs read, which goes and checks the result, right? And if we got no object, right, if there's no object where we went to go do this thing, we basically zero fill the page and then pass it back. Ditto here if we've got if we've got different errors, then we will handle them as well. And then eventually we call this netfs subrect terminated, which will then go and write or finish off the request. Okay, so now we've done a write begin. At that point, we pass it back to the netfs and the BFS layer. It will go then take the pages that it got from userland and copy them into the page cache pages that we're using. And then we call ceph write end, or then write end will get called. And this will go and set the pages up to date so that the page cache knows that it can satisfy reads out of these pages. And then we go and may need to go and increase the size of the file, which is what this does. Because if we wrote to the end of the file, now the file's longer, we have to go and do that. And we have to mark these pages dirty. And so later on, the kernel will turn around and write these pages back to the server. At this point, all we did was we read in with the unwritten parts of the page, did copy the data into them, and then we marked the thing dirty so that we can write it back later. And then at a point, we unlock the pages and put them, and then we might also check and see if we have caps we need to deal with at this point. From there, now let's say, okay, we've got the page in the page cache, okay, the data in the page cache. Now we're later on, let's say someone calls sync, right, or fsync or something like that. Now we have to write them back. And at that point, what we do is we do something called, usually get a call from the VFS to do something called write pages. And we have the ceph write pages start vector that will do this. And what this thing does is it walks down the tree of pages that we've got, or the array of pages that we've got. Not really an array, but it looks like one. And it will set them up to be written back, and then start. And so you can see in here where, sorry, I'm probably going kind of fast, but But there's a bunch of special cases here. Oh, if we're beyond the size of the file, we may have to invalidate some things. Might have to deal with snapshots. It's pretty complicated. But essentially, at some point, we will come down here, set the page write back bit in the page, which basically tells the kernel, hey, I'm writing this thing back. And then we clear the dirty bit for the page. And that means that if someone comes in later, and dirties the page again, then we will ensure that it doesn't, that we didn't miss an erase and miss the write. And then so anyway, we gang up a whole list of these pages. It's going to walk down while it does until we are finished writing back what the VFS says it wants to write back. So we gang up a pile of these pages, and then we call CephOSDC new request. So we generate a new write request. In this case, you can see write. And then if that turned out to fail, because sometimes allocations in the kernel can fail, we have to deal with that as well. And failing during writeback, or failing allocations during writeback is particularly problematic, because a lot of times we're writing back data because we're trying to clear memory. So if we are under memory pressure and we can't allocate pages in order to write back data, then we have a big problem, right? We can't go anywhere. So in any case, we set our callback at the end to write pages finish, because at the end of the thing, we're going to need to handle some stuff. We need to handle the end of the write. And then we go and start marshaling up pages, and that's what all this junk. This will, stick the data pages into the write request, update the extent in there, and then down here we will come down and wait a minute. There's a point where we can start writing earlier. Right here, I think. Oh no. Anyway, down here we start the request, and then this thing will kick off the write request. Interesting bug on RC. That's not free. So in any case, we will do all this. That will kick off the request and back to the thing, and then we do a little bit of post-processing at the end of that, and then we'll return. Eventually, we will come back, call the OSD client engine will submit the request to the OSD and collect the reply, and then eventually it will call, when it gets the reply, it will call write pages finish to finish doing it. And then at that point, it will come down here, mark the pages clean, or end the write back of the page. As you can see here, we're end page write back. And so we can tell the kernel that, okay, it's not under write back anymore. We might update some metrics, and then we put whatever cap refs we've held, because we take references to the buffer caps while we're doing all this. And then eventually we put the request and then the thing finishes. Write is done. Okay, so that's all fine and dandy. So that's a good example of how complex it can be to actually write out data. Reading is also pretty complex in the same way. But in addition to all that, we also have some sort of more autonomic stuff that we do. Some more autonomic activity that sort of happens in the background or that is driven by the MDS. So we've got this, so I mentioned that Ceph connection earlier. Each connection has what's called a dispatch routine, or a bunch of operations actually. Just like we have operations for the inodes that are handled by syscalls. When we get certain socket activity or certain connection activity, we will call different operations vectors in this struct. And so, for instance, like for the MDS, this is the MDS operations vector. We will call MDS dispatch. And you can see here, we've got a bunch of stuff that we do depending on which sort of message comes in. So like, if you get a reply from a request, and it will handle reply. If you've got caps, we've got to handle caps, so on and so forth. Caps messages in particular are a big part of Ceph. Let's talk about those for just a minute. So here's the thing for handling a cap message, but how do we store them, right? So caps are, we have a structure, an object that we track just like everything else to represent a cap, and these are held in an RD tree in the inode. And so when we get, say, a request from the MBS to say, flush some, maybe we wanted to, to start writing, to say revoke some caps or to grant some caps, we get this call from the MBS handle, and it will call Ceph handle caps. So like on an open or something like that, we might add some cap structures to it, and then when we, just in the response to the request itself, to a normal MDS request. But we also can get an asynchronous grant from the client, say, hey, okay, maybe some caps came free that you had requested earlier. Here they are now, and this is the part that will handle all that. So we get a cap message, and we've got a bunch of message version stuff. The Ceph protocol is a bit of a mess in that we grow the certain structures in it all the time. So if we get, depending on what sort of cap request we get, there's a switch statement here for certain types of cap requests. And then, here's the thing. And like, let's say, for instance, if we get a cap op revoke or grant, we're going to call this thing, which is handle cap grant. That does, basically we'll walk down the tree and handle all the cap grant or revoke. And at the end of that, we might end up kicking off write back. Particularly, like, let's say someone revoked or someone tried to open the file that we had open and had buffered a write for before we had written back. We might call, and then all of a sudden buffer caps get revoked. We have to then kick off a write back before we can return those caps back to the client, to the MDS. So in any case, all this is handled here, and a lot of this is handled in FSCeph caps.c. There's a whole bunch of routines for asynchronous cap requests from the server, or for doing things like returning caps to the MBS. Let's see. That's really about all I had to go over. Sort of the 10,000-foot view of the client. It gets pretty complicated, complex down in there, and that maybe give you at least a start on what to do. Does anybody have questions?
Jeff, you're talking about page write-back errors, right? And I know, like, a few years ago you worked on that, something generic for all file systems. So, can you briefly say what was the solution you came up with to handle errors when you're trying to write back pages?
So essentially what happened, that's not really directly related to Ceph, but I can talk about effectively, right, when we have, when you write data to the inode or to the page cache, right, eventually we have to write it back. But a lot of times that write back can happen behind the scenes. Like, you might not even be aware that, it's doing maybe flushing pages out because of memory pressure. But at some point, the idea is that you will call fsync, and then at that point, if there's an error, and so let's say you're writing back because of memory pressure, right? When you get an error, you can't just return that error right away, right? We have to store that so that we can report it later. And so there's so we put some infrastructure in several years ago called Aeroseq, which just sort of splits up an integer that we track in the inode that just it's like both can hold an error up to like negative 4096 or an error of 4096, right? And then from there and then the rest of the 32-bit integer will hold a counter, and that counter tells us whether this is whether this error is a way for us to tell whether this error has been seen yet or not on a particular file descriptor. I could go into that. It's a little more complex, but so essentially what we did though, so when you there's actually a documentation file that may be a better I'll have to find it. Yeah, here it is. So here's like, if we have a 32-bit integer, right? We have something here called, we declare, 12 bits of that to represent the error node that we're going to store. Usually, like when we store an integer, right, we have a bunch of bits left over if it's just going to store an error. And so what we decided to do is just use the rest of this to store a counter and a flag too, to see whether the thing has been seen yet or not. And if you go read this, it'll explain how it sort of works, right? But essentially what it is that we keep a copy of this. So when an error is recorded, if we will bump this counter every time, right? So let's say you wrote back once and you got an error, okay, and then someone called fsync, right, after they did their write, and then maybe you write back some more data and you get another error, right? And then it's hard to tell whether if you call fsync 2 times in a row, you don't want to report 2 errors in a row before there's not been another write back error. And so what we want to do is ensure that we report each error only, report the latest error only once for each fsync or msync or whatever. So yeah, I mean, essentially we have this counter in here, and then we have this scene flag. And so all this thing does is it just, in each struct file, we keep another 32-bit integer, and we basically take a snapshot of whatever the thing was right after we did the fsync. So like if you do an fsync, we take a snapshot of what it was at that time, and we report, if it looks like we need to report an error, we will, based on, whether, and then when we look in the struct file version of this counter, we will, if it looks like this thing has already been reported, we will just report 0, right? Because there hasn't been a write back error since the last time we called fsync on this file descriptor. But if there is, then say there is a new write back error, we will bump this counter, and then when we go to write back, we will compare it to the one that's in the struct file from the last time that we did it, and we say, well, the counter got bumped, even though the error number is still the same. We're still we know that there was a new error that was recorded since the last time we reported this error, and then we can report an error again on the subsequent fsync. So that's the idea, basically, is to allow you to record errors in one place, but we can report them over multiple file descriptors. Does that sort of answer your question? Or I could probably give a whole talk on this alone. But
Okay, Jeff. Yeah, thanks. I'll look up this documentation. I mean, I had this question when you're talking about how hard is the issues that you might hit when during a page write back. So I thought of this.
Yeah. So the problem we used to have, right, was that we tracked a lot of these errors. We had actually basically had a flag that was just in the inode, and so what would happen is, let's say you might have this file open multiple times, and lots of people are writing to it, and then we would like the write back error happened, we would just set that flag, and then whenever someone called fsync, then they would see the error and clear the flag, right? And then so if another file, if another person calls fsync on a different file descriptor, they wouldn't see an error, right? And they would think that, oh, my code must have, or my writes must have gone through. They were fine, right? But they might not necessarily the case. And so this was the mechanism that we came up with to basically ensure that whenever whoever is writing to, when you have people writing to multiple file descriptors on the same file, that they all will see errors, if there was one, so that way they ensure that it's reliable to ensure that you will that we report errors to everywhere. So, but yeah, take a look there. If you have questions, let me know. I'm not sure how applicable this would be in any, but it was an interesting project. Any other questions?
Hey Jeff, quick question. Do we use Reader Plus in the kclient?
Yeah, we do. We do. We've got there is no real Reader Plus operation in the kernel. So, you just do a reader. But what we do is we will do a reader, and then we will pre-populate inodes and dentries in the dentry cache and in the inode cache when we do that. Here I can show a quick look at Ceph Reader. I didn't really go over how lookups and stuff work, but yeah. So we have a reader. Notice it's called iterate now, but reader infrastructure is actually pretty complex at the VFS layer. But yes, essentially when we get info back, we also get back, when we get a list of dentries, we also get inode info for them as well, usually. And so, yeah, we will pre-populate the inode cache. We'll allocate inodes and pre-populate all the info in there. And so that later when someone goes to do, like, say, a stat or something like that against that particular dentry, we don't need to go to the server for it because we've already got it in the last reader request. So yes, we do we do sort of a reader plus.
Okay, so I remember some time ago there was this reader p call added. That in one call you can fetch the directory entries and the stat information too. I mean, currently doing a stat obviously fetches the stats for an inode from the D cache or something. I mean, from the kernel cache. But this was one call that fetches the dentries and then all the stat information for those dentries. I mean, it was added in Fuse if I was not wrong, but maybe it was added to VFS and every other file system added. Not sure. But looks like we don't do.
Sorry, were you talking more at the reader, or are you talking more at the VFS layer? So like, was there is no reader plus system call.
Okay.
And so we don't have anything like that. Now, the NFS server can do may get a reader plus request, an NFS v4 reader request is also like reader plus, right? It also fetches inode info.
Okay.
So
probably saw some patches going on that tried to add it to the VFS, but probably they didn't make it. Okay.
Yeah, they didn't go in. I mean, we did add StatX a while back, which it's like an extended stat thing, right? And there's been some discussion about doing a reader plus operation, but it's not real clear, what applications will use this, right? I mean, I could see it being used by like Samba maybe, or the NFS, usual and NFS servers maybe, but it's not as useful as you might think. And so, and effectively, I mean, the only thing that you will, because, like we are populating the cache when we do a reader in the background, right? So say we get a reader request, right? We will go ahead and get the list of dentries that are in the directory, but we'll also, the MDS will also forward along a lot of the inode info as well for each of those inodes. so again, we populate the cache for that. So, if you do a reader plus system call, the only part you're really saving you is that the context switch from the multiple system calls, right? With something like a Ceph, right, where the time that you are spending in that is pretty negligible. Most of your time is dominated by the round trips to the MBS. And so it turns out not to be as big a win as you might think it would be to just cut out that sort of system call activity. It's a bigger deal if you've got something like on a local file system, maybe. There was some talk about that. That's really where I think you would see it. Like, if you wanted to do, like, XFS would want to do that, because then you could do something that's because it's pretty fast, right? Dealing with local disk, and so you don't need to do cutting out that system call overhead, because anytime you do a system call, you have to do a context switch, and so the cutting out that system call overhead can be a big deal there, but less so in the network file system. Paradoxically, in a way.
Right.
Any other questions?
Yeah, it was probably related to XFS. There was someone added a bulk stat call or something, but I'm not sure if those made it. But it was on the similar lines of getting a list of entries and all the stat information, so you don't have to do the stat call again. So yeah, I think so. You're coming from the same lines.
Yeah. I mean, we did talk about it a while back, and some of the Samba guys were kind of gung ho on the idea, but it didn't go anywhere, because I don't think it's as useful as they think it would. I think nowadays you might be able to do something like that more with and Samba's sort of moving into using more IOU ring, which is another way you can do IO now. So that's all that stuff, and so they're doing some of that sort of thing in IOU ring. And so I think there may be a way to do a reader plus an IOU ring, but right offhand, I don't remember exactly how you do it. Okay. Any other questions or comments, feedback? Okay, if not, I'll take that as a no, and thanks for your time, everybody. Have a good day.